Hello, so my model was created based on the chronic kidney disease dataset that was publicly available in Kaggle. For my paper, my hypothesis was that the accuracy of the model that I would create would not be greater than 95%. And to start out, I did some data pre-processing and prepared the data for analysis and modeling. So here, what I did, I imported some Python libraries that are used for like numeric to do like analysis and data visualization. So this was the first of the data sets that I imported. This is the kidney disease data set. And right here, you see me taking a preview of it. As you can see, if you look on the features, they're all abbreviated and basically gives no meaning. So the second data set that I'll be importing, that basically has the unabbreviated feature names. What I'm going to do, I'm going to show you what the data set looks like before the renaming was done. So if you can see, this is not really a good depiction, or it doesn't tell a full story of what is contained in the columns. So that was the purpose of the description data set. Right here, you see me manually naming the columns. It looks way more presentable. I did not remove my columns. Perfect. So this is a preview of the data set after, we've renamed the columns. So the first thing I decided to look at was the data types for the features that I had in the data set. If you could look on the data set, you'd see that packed cell volume, white blood cell count, and red blood cell count are listed here as objects, but we all know those are numeric values. So what I did, I created a function to convert the data types to numeric. Well, I made use of Python's toNumeric function to make it way more easier. So that's what I did here. This was the function I created, and this is me converting the three features to numeric. Right here, I took a look at it again. As you can see, it's float, so it has been changed from object. Also, I decided to drop the ID column because in pandas, what happens if you look right here, an automatic index column is generated, so we can get rid of that ID column. So that's what I did right there. And this is me just taking a preview of the data set to make sure my change has gone into effect. Right here, I'll be separating my columns into numeric and categorical. What I'll be doing, I'll be looking at distribution of my numerical columns, and I'll be checking my categorical columns for any dirtiness. So I created a function that will do the extraction for me. Here are a list of my categorical columns. Here are my numerical columns. So right here, I'm making use of Pandas' unique function. So what that does, it returns all the distinct entries that are within a column. So after running it, I realized that the diabetes mellitus, coronary artery disease, and class all have a little dirtiness. As you can see, you have the tab symbol that is part of some of their entries. So those will actually be treated as unique entries when they actually aren't. So we're just going to remove that tab from these entries. Right here, I'm making use of, Pandas' replace function to do that for me. After doing that, I'm going to run the function again to see if my change is in effect, and it is. If you look there, there's no tab in the entries. So now I'm going to take a look at my numerical columns. As you can see, I have 14 of them. Right here, I'm doing a histogram so we can analyze the distribution. As you can see, a few of our features have skewness. Let me speak as to the ones that I had mentioned. after observing the distribution of the age feature, which is right here, we can see that it is less skewed. You can see the data moving to the left side, which means there's some kind of negative outlier. There's some kind of low value outliers. This is also the case of the blood pressure feature, where we see that it's slightly right skewed, which means there's some kind of high positive outlier there. What I'm gonna do, what I did here was that I created a count plot of the categorical columns so I could check on the balance of the data. As you can see, there's clear imbalance that is in the data. If you look here, if you compare the amount of entries of normal to abnormal, it's pretty imbalanced. Also for coronary artery disease, there's also imbalance. So there's a lot of imbalance here. So the target feature for a model will be class, because that's what has if someone has chronic kidney disease or not. So we also did a check to see how much imbalance was in this data as well. So now what I did was that I created a heat map, and this heat map contained the correlation because we wanted to see how correlated the columns were with each other. So in the heat map, we normally say like anything over 0.5 is normally good correlation, and over 0.5 or less than negative 0.5. So as it relates to specific gravity in red blood cell, let me point to that specific gravity in red blood cell. You see there's a 0.58 for the correlation, which is pretty decent correlation. Another example of good correlation is between packed cell volume and red blood cell count. So here we're just doing some descriptive statistics. I decided to group on red blood cell in the class, and I'll be looking at mean, median, min, max, and count for the red blood cell count of that group. Right here, imported the Plotly. What Plotly does, it used to do data visualization, but the visuals are more dynamic, meaning you can touch them and it changes as you touch it. So I decided to look at the distribution. So I decided to use a volume plot, not for any specific reason. I could have used any other plot, but I just decided to, add some variance to the type of plots that I use. So what I was comparing was the red blood cell and the class. So I was looking on how many persons had CKD, that's chronic kidney disease, to how many did not, based on red blood cell count. So as you can see from here, for CKD, which is represented by blue, the red blood cell count, as you can see, this is approximately 1 point something. Yeah, this is basically 1. So basically 1 to 8, the red blood cell count. And for not CKD, you can see this is from, let's see if I can get, so basically a little under 4 to 7. So that was the range for the red blood cell count. So right now, I was looking on the relationship between hemoglobin and packed cell volume, also analyzing the distribution of red blood cell count for chronic as well as non-chronic. And then we're going to do some analysis. So what we're basically doing, we're just looking at features because we'll eventually be creating a machine learning model. So we want to see what the relationship is like between the different features. So I decided to create a scatter plot between hemoglobin and the packed cell volume features. As you can see, it is pretty linear. So we can see there's really good relationship. As hemoglobin increases, the packed cell volume increases as well. This time I decided to use Seaborn's facet grid plot along with the KDE plot to create a plot that gives us a distribution of the red blood cell count as it relates to the different classes. As you can see from the facet grid, that persons who do not have chronic kidney disease have a higher probability of having a higher red blood cell count. And what I basically did right here was that I created 3 functions: the volume plot, scatters, and KDE plot, basically because I did not want to keep on continuously calling these functions, so it helps give me a lot of automation. So this was me here checking to see if that function was working. This is me just finding the KDE plot and a few different features just to see what was there. This is me just doing more visualization. I'll just skip through this because it doesn't really give us any specific analysis. This was just me just testing it out. And this is me still just observing relationship between the different features. Okay, so now I'm doing some data cleaning to do with the missing values, because machine learning doesn't really work well with missing values. So we're going to try to get rid of those missing values. So basically what I did here was I looked for each column and I wanted to see how many missing values were in each. As you can see, red blood cell and red blood cell count had a lot. So what we're going to try to do, we're going to try to deal with these missing values. So one way I decided to deal with it was random value imputation. There are other ways such as mean, the mode, but with this many missing values, I just thought it was best to use random value imputation. So this is me just creating a copy of the data so that I can use it without really changing the data frame that I had before. So this is me making use of Pandas's sample method, which basically just gives me it will basically do a random drop for me, right? So basically, because I will be testing it out on the red blood cells, I'm going to try to drop all the missing values in the red blood cells. As you can see, there were 152. That's why that 152 was here. As you can see, we have results here, which means that we have something for those 152. We have 152 entries. What we now have to do, we have to make sure that those entries, the index for them match the entries for our data frame. So now we're getting our index entries. And this was the index for a random sample. So what we're going to do, we're going to equate them to make sure that when we're doing a replacement, it replaces the indexes that were empty. Perfect. Now we're taking a look at the red blood cells feature again. As you can see, we no longer have any missing features. So what we're eventually going to do, we're going to apply this on all the features so that eventually there will be no missing values in our data set, so we can move on with our machine learning. As you can see, I created a random value imputation function, which will basically automate this for me. So what we're gonna do right now, we're gonna check the missing values, and we're gonna on the categorical and numerical features, and we're gonna use feature encoding. So basically what it does, it just assigns an index for each unique entry that is in a feature. So now we're taking a look at all the missing entries in numerical columns. We're applying a random value imputation function that we just created to them. As you can see, we no longer have any missing entries, so our function is working. We're looking on the other categorical features that have missing entries because we'd only done it on the red blood cell count. As you can see, it is only the pus cell that has a lot. So what we're going to do, we're going to apply the random value imputation on this. But we'll be using the mode. We'll be for the other cells, because they do not have a lot of missing entries. We do not have these random value imputation. So we'll be using the mode to take care of that missing data. So from this, you can see that we basically just need to fill the not present entity. And this is just creating other functions, checking to see that our function is working. This is us just checking to see the unique entries or categorical feature. So after doing some reading, I realized that feature encoding is really great when there are 2 or 3 categories, basically when the count is low. So that was another reason why I decided to use this method as well. So this is me importing it from sklearn. And this is me applying it to our data. So as you can see, none of our features have any categorical columns anymore because the labeling coding was able to replace those entries with a value based on their position in the column. So what we're going to do right now, we're going to select the best features because we're going to be creating a machine learning model, but we obviously can't use all the features. So we're going to look for the best features that we can use for a model. And thankfully, sklearn has a package, select k-best, which that will help us. And that selection will be done based on the chi-square test, which are important as well. So what I'm doing right here, I'm separating into dependent and independent variables. Obviously, our class will be our dependent column because that is what will be dependent on the other features. So here I'm just assigning them X and Y because that's just what is normally done. That's what everyone is used to. So for easy understanding, I did that. As you can see, these are all the other columns. And as you can see, this is our class, which is now has an alias of Y. So this is me just calling on our select k-best function. And what it does, it returns an array of scores. So what we're eventually going to do, we're going to select the best scores. I decided to use the best 10. You know, I could have used less, I could have used more. I just thought 10 was a really good score to work with. And we'll be storing these scores in a data frame that will be created called data scores. You can see here. So I created a column with all created data frame with all the columns, and I'm eventually going to concatenate the scores from the select k best method with those columns. So there you can see the different columns on their score. As you can see, the ones with a better score will be the one that will more than likely be best for our model. So as I said before, I decided to use the 10 best. So these were the 10 best features. And I basically just store them here in my selected columns. Perfect. Then right here, I'm creating a data frame with the 10 best features. And this is me just looking at the dimension of that new data frame. So what I'm doing, I'm creating a cross-validated model. What I'm going to do, I'm going to predict and check the accuracy of the model using sklearn metrics classification report. So right here, I'm just importing the train test split because we're going to have to divide up the data into training and testing sets. As you can see here, I'll be using a testing size of 25%. I'll be taking a look at my train and my test. As you can see, 300 and 100 is pretty consistent. 100 is 25%, so nothing wrong there. Everything looks fine so far. Right here, I'm just looking on the values. As you can see, it's not too imbalanced. It's 188 compared to 112. Just a little imbalance, not too much to throw off our analysis. Here I'm installing the XGBoost machine learning model because that's what I'll be using to do my prediction. So this is me just looking on the parameters to see which ones I'll be using for a model. So there I just fit the training data to our model. And right here, I'm looking for the best model. So that's what random search CV does for us. It looks for the best model. So that's some good automation there. And I'm also have the best params method, which helps to select the best parameters for us as well. So what we're going to do, we're going to use the model that was suggested, and we're going to use the parameters to create that model for us. Here we're just fitting that in our model. And right now we're going to test how good our model is. So we're calling the predict method, and that's what it returned. So now what we're going to do, we're going to evaluate the model performance based on these results that were returned. So I'll be using sklearn metrics. So some things I'll be importing is the classification report, precision, recall. Some of these should be in the classification report, but just in case it wasn't clear enough, I imported them as well. So right here, I'm doing a confusion matrix. As you can see, we have 61 here and 31 here, 1 and 0, which means a pretty high number of predictions will be correct. Right here, I'm calling the classification report to see how well our model performed. As you can see, precision is 100%, which is excellent. Really excellent. Accuracy 0.99, recall 0.99, which is really good. Right here, basically just calling individual metrics from that classification report in case it wasn't very clear. As you can see, our accuracy 0.99, precision 0.98, recall 0.99, F1 score is 0.98, which means our model performed really well. Not only that, I was able to refute my hypothesis that my model will not perform better than 95% in terms of accuracy. Here I see an accuracy score of 99. So after evaluating the model, I can confirm that the model performed well and it achieved an accuracy of 0.99, precision of 0.98, among other good metrics. Therefore, my hypothesis of the model not being greater than 95% has been refuted.